Well, this is the 9th video on Organic Chemistry 2 topics, and I just wanted to take a little bit of time before we, go into a lot of different reactions to focus in just one more time on structure. Learning how to see resonance forms. If you know how to see resonance forms within a structure, you're ready to take on the reactions that we'll see here in the, second half of this set of videos on what typically is seen in a Organic Chemistry 2 course. You also want to know a little bit about aromaticity now, and we've covered this structural feature of cyclic compounds that give it a little bit more stability. So resonance, aromaticity, inductive effects, it is so important before we go out into a lot of different reactions in OChem 2 that we know structure well. The first reaction we're going to consider in this next 3 videos here, including this one, is going to be alcohols, where we have some alkyl group or hydrocarbon connected to an OH group. And then we're going to consider something that reacts a little bit like it, a little less reactive, is an ether, where we have 2 alkyl groups bonded together through an oxygen. This is called an ether. And then the last one we're going to consider is a special type of ether, where we have a ring, a strained ring, 2 carbons bridged by an oxygen. Kind of looks like an ether, but it's a special type. It's called the epoxide. The epoxide has special reactivity because it has this ring strain. So we're going to start looking at reactivity of alcohols, ethers, and epoxides in that order. In this video, we're going to just introduce reactivities of alcohols. In the second one, we'll look at these 2. After that, the videos will start looking at benzene. And benzene's unique in that we can not only use it to go and attack an electrophile. That is, we can use this pi electron density in benzene, even though it's an aromatic ring, and we may have to add a catalyst to this electrophilic compound. We may have to have a catalyst because of its stability. We can still have it act as a nucleophile, so the benzene ring acting as a nucleophile. But we can also take a benzene ring and have off of it a chlorine and maybe an electron withdrawing group, strategically placed, an electron withdrawing group like a carbonyl, and we can have a nucleophile come in, not an electrophile, and do the attacking. So we're going to see what we call an EAS reaction, electrophilic aromatic substitution, where we attack an electrophile, and we're going to see an NAS, where we have a nucleophilic site coming in to attack the aromatic ring, and we get a substitution. So we're going to see EAS and NAS in the next sort of block of reactions that we consider. So first, second, and then let's keep on rolling. We can have carbonyls with leaving groups that we can attack with nucleophiles. We're going to focus in on this sort of 4 o'clock to 6 o'clock or range. We're going to have a lot of reactions wherein we attack the carbon of a carbonyl that's connected to a leaving group. Or consider that same nucleophile or something like it, where we attack a carbonyl that has just alkyl groups or hydrogens, no leaving groups at these positions. That's our next big block. So 3, alcohols, ethers, epoxides. Then we're going to head into EAS and NAS involving aromatic rings, where they're the focus, the star of the show. Then we're going to move into carbonyl chemistry, substitution chemistry, acyl substitution. This is called acyl addition. So we're going to have types, and then we're going to take and have reactions wherein we take electrons from, a proton from the neighboring carbon, called the alpha, position of this acyl or a carbonyl. We have an alpha position, and we're going to do some reactions where we go and attack electrophiles with the alpha carbon that's made negative. So what we're going to get is alpha additions, alpha substitutions. We're going to do some chemistry, some really neat chemistry through the alpha position of a carbonyl. And there's some variations on this using amines, enamines. We'll see some really neat chemistry that can be done at the alpha position to a carbonyl, where we can attack an electrophilic site. Then last, this set of videos on reactions is going to sort of wind down, where we're going to look at amine chemistry, reactions to form or react amines that have, let's say, one hydrogen and two alkyl groups off of a nitrogen, so amines. And then last, we're going to look at oxidation reduction sort of as a capstone on all the reactions that we've covered in OChem 2 or in most of your OChem 1s, just a review of all the oxidation reduction reactions, and even consider some unique organometallic reactions. Folks, if you make it this far in this set of videos that I'll be presenting from here on out on reactions, if you make it this far, we're going to probably focus most on just what product is formed given certain reagents, and not so much on the mechanism. But folks, as we go into the 4 blocks here, alcohols, ethers, epoxides, benzene rings, whether it be EAS or NAS, carbonyls, whether it be acyl substitution or addition, and this alpha position or alpha substitution chemistry using the alpha carbon to a carbonyl to do chemistry. Those 4 blocks we're going to do a lot of mechanistic or have a lot of mechanistic discussions. Well, to keep this video short, what I'm just going to do is introduce the naming and properties of alcohols, and then we'll get into, in the next video, reactions of alcohols, and in the third one in this block we'll consider ethers and epoxides. So 3 videos for this block on alcohols, ethers, and epoxides. So 3 videos. So let's go ahead and finish up this one just talking about the naming and properties of alcohols. So alcohols have a higher priority than alkenes or alkynes. So alkenes, double bonds, or alkynes, triple bonds, don't set the priority of the name of a compound over that of an alcohol. So if we have an alcohol present, we try to give it the lowest possible number in the longest continuous chain of carbons. So for example here, I've numbered this carbon here as 1 because the longest chain is 6 carbons long, 6 carbon long chain that has the OH group off of it. That's important. We can't just count the longest chain that doesn't have the OH group off of it. We have to find the longest chain that has the OH off of it. So 1, 2, 3, 4, 5, 6. We could have considered this position or this direction 1, 2, 3, 4, 5, but that doesn't have the longest chain with the OH off of it. This is the longest chain, and the OH is off this end closest to this carbon, so we give that carbon the lowest number possible. 1, 2, instead of 1, 2, 3, 4, 5, we want this OH to be at the lowest number possible. So we've numbered 1, 2, 3, 4, 5, and 6. So then we can kind of throw in those rules you've already learned, maybe having watched other videos or taken a first semester organic chemistry course. Now we know where everybody's located. We have a chlorine at the 3 position, so we can call that 3-chloro. We have a bromine at the 4 position, 4-bromo, and I'm just naming the groups off the branch. We'll put it all together at the end. And this is a little more difficult. We have a chlorine off of a carbon that's off the 3 position. But that carbon also has a methyl group. So maybe you don't remember, or maybe you haven't learned, but if we have a branch that's off this parent that I've circled here, that has a branching within it, so instead of having a straight chain, we have another branch within the branch, we have a complex group. And you can name it by taking this carbon at the first position off the main parent, and we kind of call it our subparent. We can say that's an ethyl group. And off this carbon, which was always 1, the first one off the main parent is always carbon 1 in this ethyl. So we can say 1-chloroethyl is the name of this whole group, and it's off the 3 position. 1-chloroethyl is the name of the whole group, so it's in brackets, and then we have 3 out in front. So 3,1-chloroethyl, 2-hexanol. So let's put all that together, underlining the letters that set the alphabetic order. Bromo, chloro, we'll put this one first since it's the shorter, and this one second, or third after that. So we have 4-bromo, 3-chloro, 3 should be a dash there, 1-chloroethyl, and then 2-hexanol. What's that 2 indicating? The OH group, which gets the priority. It sets the parent's name. The parent's always at the end, his children are in front of him, or his groups, substituents off, are in front. It sets the ending of the name. So 2-hexanol, because the OH is off the 2 position. So here's some just other rules. If we have multiple identical groups, we can use di, tri, tetra. These are not considered alphabetically, remember that. We've already covered the longest chain has to include the OH. We want to always have the larger number of branches if you ever have 2 parents that have the same number, 2 chains that have the same number of atoms and also include the OH. You want to try and find the longest chain that has the largest number of branches. So that's just some review of the naming for alcohols. Let's look at the properties and we'll be done. So this is interesting. Alcohols, unlike ethers or epoxides, when we have an OH or an NH group present within a molecule, you have the potential, or I guess you have, in a solution of, or if that's in a substance form or a solution with water, you have what's called hydrogen bonding. This is a special, stronger type of dipole-dipole interaction. So hydrogen bonding is unique to those compounds that have NH or OH bonds within them. And of course alcohol has that. So we've just drawn a simple picture here of 2 molecules of an alcohol that could have some aggregation or some intermolecular interactions that are weak. Maybe 5 kilojoules per mole is sort of your bonding strength, whereas the covalent bonds is around 100 kilojoules per mole. So 5% of a covalent bond, sort of the strength here. This oxygen of one alcohol is partially negative, and it's lined up or across from a hydrogen that's partially positive on another alcohol. That's what really the hydrogen bonding looks like, and we can get, of course, more of these alcohols to aggregate together and have their OH tails or ends together in some sort of interaction. So we can get some of these either micellar shaped sheets, strings of hydrogen bonding within a solution. It's pretty cool stuff what they can do with hydrogen bonding, and of course our body uses it to fold proteins or amino acids to make proteins, DNA folding on itself or helical structures is really set in part by not only the covalent bonding but the intermolecular interactions within a long polymer chain of protein or nucleic acid. We can have that fold in on itself, driven or directed by, in part, hydrogen bonding. Alright, so that's a special type of dipole-dipole interaction. Don't forget, kind of lower in strength of interactions is dipole-induced dipole interactions and induced dipole-induced dipole interactions. So we can have sort of these 3 and then a special type of hydrogen bonding, or a special type of dipole-dipole interaction, which is hydrogen bonding. So kind of the 3 categories and then the special type of dipole-dipole. And you say, well, what's an induced dipole interaction? It kind of is occurring when you have, if I can just be kind of general here, if we have 2 atoms that are weakly bonded together, X and Y, and their bond, the electrons can be easily moved around. It's kind of like when you have bromine with bromine here, or I guess it's bromine with iodine. If we were to take another molecule and have it flipped, we could have inducing of a polarity in this bond, which at the same time as it's starting to interact would induce a polarity over here that would be opposite. So we could say partially positive if electron density is pushed and it's not easy, it's not too difficult to push it, we can induce a dipole. And then of course that would interact with compounds around it such that it would be an opposite flow. Electrons would flow this way to interact with the partial positive end of another molecule and create a partial, as electrons move that way, opposite charge on the other end. So we can get some interactions. That would be an example of induced dipole interactions. You see it in your cases with iodine, bromine. They're very weakly bonded to whatever they're connected to, carbon-iodine bond. We could have inducing of polarity within this bond, which interacts with another bond that's done the same thing. That would be an example of where we could see induced dipole interactions. Alright, let's go ahead and finish, I guess, and just simply say this, that when we have hydrogen bonding, which is a special type of dipole-dipole interaction, it's a much stronger type of interaction than when we see it with induced dipole interactions, London forces or whatever. But let's remember that because we have not just two molecules, but millions and billions of molecules in a solution, these can start to add up. So we can have some pretty significant effects of either induced dipole interactions, or more so, hydrogen bonding interactions can change a solution's property because we have a cumulative effect of all these little interactions. Well, that's it. We've looked at the naming of alcohols, we've looked at a little bit of their properties, and we've also, just to come back, kind of given a view of where we're going. We're starting in this first block on alcohols, going to move to benzene, move to carbonyls, and then move to the alpha position of a carbonyl to do chemistry. And then we'll close it out with just a very brief discussion of amines, oxidation reduction reactions, and organometallics. That's it. Bye-bye.